In this video, we're going to take a look at stoichiometry that involves chemical reactions that include gases. Now, you are already quite familiar with applying stoichiometry to chemical reactions. So the only difference here is that this chemical reaction will include a gas as either a reactant or as a product. So let's take a look. You're very familiar with this diagram now, which maps out the conversion of, let's say, the mass of a chemical A to, let's say, if you were producing chemical B, and what mass could you produce? And understand that in order to do that sort of conversion, we have to make use of our balanced chemical equation, the stoichiometric coefficients, and being able to convert the masses to moles. Typically, the conversion involves using the molar mass, so mass in grams to the amount of substance. Or once we know the amount of substance, let's say of chemical B, we can use, once again, the molar mass to determine the mass of chemical B produced. As mentioned, we make use of the mole ratios based on the stoichiometric coefficients. The difference here is now we're going to include information about a gas. And that information can be given in a variety of ways. It can involve volume, pressure, temperature. Often volumes of gases are given. And so, for instance, if we knew the volume of chemical A and we wanted to find out what mass of chemical B or what volume of gas of chemical B, the first step would be to take the ideal gas law equation, rearrange to solve for mole. So if we know the volume of our gas, and we know the pressure, and we know the ideal gas law constant, of course, and we know the temperature, we can convert to the amount of substance. In a similar way, if we have the amount of substance, and we wish to determine what volume of gas, once again, we make use of the ideal gas law constant, rearrange to solve for the volume. And therefore, if we know the moles, we can multiply by the ideal gas law constant, multiply by the temperature, and divide by the pressure. So it's just a different set of conversions that allow us to interconvert between moles and volume of a gas. Of course, if you have the pressure of the gas, you can also interconvert in that fashion. So we'll take a look at a couple of examples of applying stoichiometry to balanced chemical equations involving gases. I do want to add one note of caution. However, when we're talking about the volume of a gas, understand that this is not the volume of a solution. This is not an aqueous solution. This is the actual volume of a gas, which of course depends on the size of the container. So here's a typical example. What we're trying to do here is produce a certain volume of gas in an airbag. Of course, these are used in cars. If there's a collision, the airbag is detonated, a certain volume of gas is produced. This protects the passenger or the driver as a result of the collision. Of course, the chemical engineers in designing this would want to make sure that the appropriate volume of gas is generated. So we would need to know, well, what mass of sodium azide is required to inflate the airbag to a particular volume. We're going to do this calculation initially at STP. So let's see how this will work. Here's our balanced equation and what we know and what we're trying to find out. The volume of gas in liters and the mass of the material in grams. Now, of course, we know some other things as well. We know that the pressure is 1 bar and that the temperature is 273.15 Kelvin. Of course, these are exact values because this is standard STP conditions. Let's take a look at a unit plan to do this particular conversion. So we're starting from the volume of nitrogen gas in liters, or at least this is what we know we want to produce. And if we know the volume of nitrogen gas, of course, we can now convert to the amount of nitrogen gas. And we make use of this rearranged ideal gas law equation. Once we know the amount of nitrogen gas, we can calculate the amount of sodium azide. And if we know the amount of sodium azide and the molar mass, we can calculate the mass in grams. So you've been through this process a number of times. Here is the worked out example. So 70 liters of nitrogen gas. The conversion involves that 1 bar, or multiplying by 1 bar, dividing by the ideal gas law constant, and dividing by the temperature. So at this point, we would know the amount of nitrogen gas. We now make use of the stoichiometric coefficient. So it's 2 moles of sodium azide for every 3 moles of nitrogen gas. And then finally multiply by the molar mass of the sodium azide. This gives us 134 grams of sodium azide that would be required. Note to 3 sig figs given the original quantities. Now, of course, it may not be so true, let's hope not actually, that the temperature inside your car is 0 degrees Celsius. So it'd be interesting to know, would we need the same amount of sodium azide to generate that same volume of gas at a higher temperature? Of course, we can calculate this, but let's do a little thought experiment. So once again, we'll grab this equation, and this represents the moles of gas that need to be produced. And if we're doing this at a higher temperature, note that the temperature term is found in the denominator. So if it's a higher temperature, I think you can see that this would therefore result in a lower amount of material, lower moles that would be required to generate that same volume of gas. If it's a smaller amount of gas that's needed, it would be a smaller amount of sodium azide that would have to react, and therefore a smaller mass of sodium azide that would be required. And that's reflected right here on this slide. So that corresponds to an additional key question associated with this particular problem. In the next video, we'll take a look at 2 more examples of typical stoichiometric problems.